And today we're talking about neural networks, to be more specific, convolutional neural networks. And we'll be mostly focusing on computer vision. And I'm super excited to hear from our speakers. We're going to take you guys through right from the introduction to the code labs, both in Python and in R. Please feel free to ask questions at any point of the presentation. Just type the questions on the chat and we will be able to see them and answer your questions. Also feel free to comment or ask for clarification. This is going to be an amazing session, and I hope you guys at the end of this are able to either learn a new skill or learn more about and reinforce what you might already know. So with that said, I'd like to ask our first speaker, Glorious, to go right ahead and give us an introduction into CNNs.
So hi everyone, I hope you can hear me. Someone can confirm if my voice is audible.
Yes, we can hear you.
Yes. So I'm going to take you through a bit of theory before Eric and Joshua come and take us through the code, right? So we're going to learn about convolutions and pooling majorly in the theory bit. Convolution neural network is a class of deep neural network which is mostly used when carrying out image recognition, image classification, and object detection. So convolution neural network algorithm has been used by many companies in their algorithms. For example, we have Facebook that uses CNN in their automatic tagging. We also have Google for photo search. So nowadays you can search for content using images. So you drop an image and then they'll show you different sizes of the same image that you've shared or the different sites where the same image has been used, right? And then basically in image classification, it's the process where we take an input of an image and we output a probability of class or classes. This will depend on the data set. Some data sets are bi-class and others are multi-class. So what we mean by that, for example, if your model is basically supposed to detect whether an email is spam or not spam, then we would have the data set being bi-class. So it will only have those two probabilities. But for instances where we have, for example, it's a model that's supposed to, for object detection, for example, the model is supposed to identify whether something is a window, a table, things like that. So if there is a variety of classes that a particular image will fall under, for that case, we'll have a multi-class. And we have to note that CNN is not the only algorithm that is used when classifying images. There are also other algorithms that are used, but CNN is preferred because the processing when dealing with CNN is much lesser compared to the other ones. The other algorithms that we have are also like neural network, boosted trees, decision trees. There are very many. You can go and look at them later on in your free time. But today we are covering CNN as I've stated earlier. And CNN has it has three layers. There are three layers that help CNN when it comes to classifying the images. We have the convolution layer, we have the pooling layer, and we have the fully connected layer. Today we're looking at two that are very important, the convolution one and the pooling layer. So during the convolution layer, the images, we are basically extracting features such as edges and corners. We're extracting those ones from the images. Let's look at a practical example. I had prepared something small. Just give me a second as I share my screen. And if you have any question, you can just drop them on the chat and we'll answer them later on. Okay. So let's get a practical example. This is a practical example of maybe, let's say this is an e-commerce website and our model is supposed to classify an image of address and be able to recommend similar addresses to a client, right? So if we take a section of that image, and it's a 9 by 9 pixel. This is a what? Yeah, this is a 9 pixel, right? So we take, no, this one, sorry. So this one here, this is a 3 by 3 dimension image, right? So if we take this one as our current pixel, and then you have the other pixel surrounding the current pixel being the neighboring pixel. So during convolutions, what happens is that we have a filter, and when calculating, we get the weights of the filter, then we multiply it by the corresponding value of the pixel. So for example, we can take 0 times -1, then you add 32 times 0, and then you add 129 times -3, then you add 43 times 0.5. When you do that for all the pixels in the image, when you take all the pixels in the image multiplied by the filter, you'll now get the current pixel. So that's what happens during convolution. And then the result of convolution is the feature matrix, which then goes into the pooling layer. And what happens during the pooling layer, there are very many different techniques that can be used when you're carrying out pooling. So we have the pool max, and then you also have the average pooling. When you're using the maximum pooling technique, what happens is that, for example, let's say this is our matrix. We will take the maximum value if we are using 2 by 2. We'll take the maximum value here being 92. Then you put it aside. Then you move to the next one. We have 128, 128, 144, 144. So we take the maximum value and then you put it aside. We do the same 142, 225, 255, and then 0, and then you take the maximum value being the maximum value was 255, right? So we're supposed to take this 255 here. That was an error. And then the next one, we have 168, 0 and 64. So we'll take the maximum value as 168. We then combine the collected value to yield a new 2 by 2 block, right? And then this one now is the result. From the two layers, what we have is that the resolution of the image will reduce, and this will help the computer when interpreting the image, right? And also the resolution reducing, what happens during pooling is that the dominant features are the ones that are extracted. So basically, us getting the maximum value of the pixels, we're taking the dominant values and we're having them displayed. So that is the only thing that is being collected during pooling. We're basically collecting the maximum values from the pixels of the image, and those ones will now result to what we have. So maybe we have a summary, right? After the convolution layer, we get a featured matrix. That is what we have here. This is after you calculate convolutions using the filters, we'll have the feature matrix, which will then go to the pooling layer, and then there we are now extracting the dominant features. So maybe I can take a question from there before I continue rambling. Any question? Or if there's somewhere you haven't understood, I'll feel free to point that out. Hello? Hello?
Hi, we can hear you. I don't see any question in the chat, so I guess you could proceed.
Okay. So I guess
I've
understood.
Gloria, sorry. There's a question that has just been posted. Please repeat why we use the max pooling. That is from Eric.
Why we use the max pooling?
Yes.
Yeah, during pooling, that you don't only have to use the max pooling, you also have the average pooling. So with the average pooling, what happens is, let me just go back to the screen. I hope you can see my screen. So with the average pooling, what happens is that we're getting the average of we'll get the average of these four pixels. Like if it's a 2 by 2, we're taking a 2 by 2 block. If it's 0, 64, and then 48, and then 192, when you get the average, then that will be the value we would have here. So we are not restricted to only use the max pooling, but the max pooling technique, but you can also use the average pooling technique as well. I don't know if that answers you. Or maybe Joshua or Eric has a better explanation to the question.
I guess, yeah, the question has been answered. A follow-up question on that would be, then when do you decide what technique to use?
Personally, I prefer using the max pooling because it's simpler, and that is my I use it a lot. I don't use the average one, and most people recommend using the max rather than the pooling.
All right,
I
thank
average.
you. Okay, thank you.
Any question before I hand it over back to you so that you can continue with the fun bit? Any question? None. Okay, so I guess it's back to you, Sandra. I'm done. Thank you for listening. Oh, I forgot to introduce myself. I am Wianzi Glorious. A UX designer by profession. I'm an open source contributor and a machine learning enthusiast. I would say that.
All right, thank you. Thank you so much, Wianzi, for that beautiful introduction. So I guess now we can get to the practical bit, and we can do some coding, some code labs. We'll start with the Python code lab, and I'd like to ask Josh to please take us through. Joshua?
Hello. Hello.
Hello. Hi, Josh.
Can you hear me?
Yes, yes, we can hear you.
All right. Okay. So just give me a second for me to share my screen. Okay. Sandra, let me know when you can see my screen.
I can see your screen now.
Right. Okay. So thank you, Glorious, for a beautiful introduction to CNNs. My name is Josh. I'm a Gold Student Ambassador. I'm also an AI and IoT tech evangelist and an open source contributor as well. So I'll be doing a simple illustration of CNN in practice and in Python. So I'm using Colab because it's easy to use it without the hassle of setting up a development environment. So I'll be using Colab, and then I'll also share all of these on the whole of these lab on GitHub, and then I believe Makena and Eric can be able to send out the link as well. So in this lab, we're going to be building a classifier. So I guess in the introduction or when a session introduction to machine learning, I guess what a classifier is was already covered. So what we're going to do is create a model that can be able to classify an image to either a horse or a human. So this will be a binary classifier because we only have two classes. So it's either horse or a human. So when you upload an image of either a horse or a human, the network should be able to identify it accordingly. So you're going to start off with a data set that contains data for human beings and also images for a horse. So that's what we're going to do. So I'm going to run the first command here to download the images, and this should take just some few seconds. So it should download these images and save them just here on this directory. So once that cell completes executing, sorry for that. So there it is, it's downloading. So within a few seconds it should be done.
Josh,
Yes.
I'd just like to request if you could share the link to that notebook on Colab so that we can follow along. Is that possible?
It's okay, that's sure it's possible. So I'm just going to share the link.
Thank you.
The people that can open. I'm not sure whether these will open for everyone. Let me try it and see. Let's see. Okay, let me try logging in with. Yeah, I just want to test out and see whether once I send out this link, it will work for everyone. Okay, this will not work for everyone. So what I can do is just like save a copy. Save a copy as in GitHub. Yeah, let me try just saving a copy in GitHub and share these. Otherwise, Colab. Just give me a second here.
Sawa.
Yeah, let me have it there. Master plan. Okay. So if you go to GitHub onto the student ambassadors, the student ambassadors website. Okay, yeah, here. Presentations. So okay, is the link. Do the audience have access to the chat? Hello?
I hope so.
Okay.
Guys,
Okay.
please let us know if you're not able to, once the link is sent, if you're not able to access it, please let us know so that we can know how best to.
Okay. So I've sent the link. McKenna, you can just try it, see whether it opens. There's this button here. Once you open in Colab, just use that one, and then it will just open automatically on Colab. Is that okay?
Yes.
So just try it out and let me know whether it works as well.
All right, thank you. Let me do so.
All right. So we finished downloading, and if I come inside here, you should be able to see the downloaded. So there is these zip horse of human, and then there is these. So this will be our training set, horse of human, and then we have our validation data set here. So after downloading it, we need to unzip. You see, as you can see, it's in zip. So we need just to unzip it as well. So I'm just going to run that command, and then you should be able to see all our data set here now. It has already done the unzipping. Here, the horse, human. So these will be our training set, and you can see if all the images are right in here. So we finished doing the extraction. Then after completing the getting our data ready, that's downloading the data, and then extract. The next thing we need, and I need to highlight something for you to see. These images are not explicitly labeled as horses. If you can see, okay, if you can see, okay, it's explicitly labeled, but what I wanted to mean is that these images do not necessarily need to be explicitly named as horses. They don't need to be explicitly, but as long as these directories are explicitly named as horses, we are sure, like, now this will help us when creating our data generator, because like this particular directory contains all horses images. So if I was like even to add a different image inside here, as long as it's a horse and it's not explicitly named as horse, it's still going to work. So like in this case, when building our image generator, we don't need to explicitly label our images as horses or explicitly label our images as humans, because they are already contained in a directory that is explicitly named as horses, and our classes will be defined because based on this, because the directories themselves are explicitly labeled based on the information that is contained in it. So we have our data already. So the next step is now to, the next step will be to create, or rather create the directories in a way that we'll be able to access them from our data generator, and we already have that here. Now what I would want you to visualize is to see whether you are able to read the first 10 items in the first 10 items, then the file names of the first items in this particular directory. As you can see, I'm just using the slicing notation here just to read from the first one to the one on index 10. So you can see these are them. These are the images with the horses, and then we have the images with the humans. McKenna, if there's any question on Teams, you can always tell me. So once we have the data ready, maybe I can just show you the total number of human images and horse images. As you can see, we have 500 images for horses training and 527 for humans. So we have our data ready. That looks okay. So the next step should be perform some pre-processing before we can build our network. So the first thing is maybe just visualize how the images look like before we apply the pre-processing, and so that after applying the pre-processing, you can see the transformation that has already taken place. So at this stage, that's when, if you want to use grayscale images, if you want to convert your images from colored to grayscale, if you want to resize them, to a particular shape, maybe 224 by 224, 300 by 300. Now this is that step, because the first step was to get the data ready. Now we have the data ready. The next step is to perform some pre-processing. And so before we perform some pre-processing, what I would like us to do is visualize some few images for horses and humans and see how they look like. And then once we apply the pre-processing, you can be able to see the difference that has already taken place. So I'm going to import the libraries that will be necessary for this. In this case, it's just the matplotlib. So that's what I'm going to do here, and then just specifying. So I just want to display the images that we have as they are. So I'm specifying how many images we'll have per row, and how many images will have, how many rows will have, how many columns will have. So, and you'll be able to see that just right here after we perform the pre-processing. As you can see, this is what I was saying, like this line of code should be able just to specify how many images, how many rows we need. So we need four rows, and we need as well 4 columns. So the first 2 rows are for horses, the second rows are for humans. So this is how our data looks like. So basically that's what we're trying to do here. Then we already can see our images right here. So the next thing, we'll define our model. After we define our model, we'll perform the pre-processing. So I just want to highlight this, the next step. So we're going to define our model, that is our CNN, and then after we finish defining our model, we're going to perform some pre-processing on the images. We're going to rescale the images. In this case, it's not necessary to convert them to grayscale. But in some case, when you're dealing with images, you might find it necessary to convert them to grayscale. Then we're going to train. So what I'm going to do is import TensorFlow. The version of TensorFlow is 2.3. That's the version we're doing. So then the next step will be to create our model. So I'm going to use a sequential model. So if you understand what a sequential model is, a model that has the layers stacked one after the other. Just maybe I can just show an illustration from one of my slides here. This is what a sequential model looks like. So this one, you see this kind of a model where you have layer by layer stacked to each other from an input layer, then the hidden layers up to an output. So this is the sequential model. So we're going to use a sequential model here, and then we're going to define several hidden layers, and then we'll have our output layer. So I want you to have a close look at this. So our first layer, you can see the way the input shape. I want you to focus on this input shape, 300 by 300. I want you to remember this because it will be very important when we are performing some pre-processing on our images. And we've specified that our input shape is 300 by 300. So this should be the size, the dimensions of our image, and then the 3 here specifies that this is a colored image. As I said, in this case, we are not going to convert the images to grayscale, so we're just going to work with the colored images. And so the 3 there, this is the 3 specifies that these are colored images with the 3 channels, the 3 channels for the images. So yeah, that will be our input shape, and that's one thing I would want you to not to forget as we progress. Then after mentioning the size of our input layer, the shape of the input layer, the other thing I would like to highlight is the output layer, which is right. Okay, before I get there, we have these hidden layers here. We have these 3 hidden layers right here. And so for these 3 hidden layers, we're using an activation function ReLU. So if you know how a ReLU function looks like, this is it. So for a ReLU function, everything that is below 0, everything that is below 0, the output is 0, and everything that is above 0, everything greater than or equal to 0, the output of that layer will be the same. So what it just ignores, it just anything below 0 is just converted. It just the output it's a 0, and then everything above 0 is the same. So like if our input will be 1, the output will be 1, but if it's -1, it's 0. Like, so that's it. So that's the activation function we'll be using in hidden layers. As well as you can see, it's the same activation function that we are using for input layer. And because this is a binary classification problem, our network, for our output, we're going to be using a sigmoid activation function. So this is how a sigmoid looks like. So these are sigmoid activation functions. The good thing about this, it's relatively continuous, and it ranges between 0 and 1. So it's a binary classification. So the output will either be between 0 and 1, as you can see here. It's continuous, ranging from 0 to 1, and because this is a binary classifier, it's best if we were going just to use the sigmoid as our activation function for our final layer. And as you can see, all of this, so we have these hidden layers. And one of the other things I would like to point out is that after every convolution layer, we have a max pooling layer. And I don't think I'll go into details about that. Glorious has already highlighted about the max pooling, but just to highlight is that the pooling function will progressively reduce the spatial size of the representation, and then this will reduce the parameters and the computation of the network. So that's why you see after every convolution layer we have a max pooling layer, so that this effectively reduces the amount of the number of parameters and the computation. It makes the network is not computationally expensive. So that's it. So we've defined our model there, and the model.xaml should just now like show you so it should show you a summary of the features of these networks. So it's a sequential. As I said, it's a sequential model, and I explained what sequential is. And as you can see, we have these. We have these we have this layer, and then, as I said, I wanted to bring this to your attention. The max pooling, as I said, it progressively reduces the spatial size of the representation. So as you can see, it reduces from 298 to 149. That's almost by half. The same way, then in this layer, the output is 147, fed into a max pooling layer. The output goes down by half. So this one effectively reduces the amount of parameters and the computational. It makes the network computationally inexpensive. So yeah. So then the next thing we need to configure, after we've already configured our model, the next thing we're going to do is specify the different metrics we're going to be using. So for the loss functions, for the optimizers, and also the metrics that we'll be looking for during the training. So in this case, we'll be using a binary cross entropy. Remember, we're using this is a binary classification, so that's why the loss function in this case we're using binary cross entropy. If this was a classifier that had more than one class, more than two classes, as in it was not a binary classifier, most likely we would have gone with something like a categorical cross entropy. But in this case, we're just using a binary cross entropy. Then the other thing we're doing is we're using we're specifying the learning rate here. So I'm sorry for that. So in this case, the learning rate, we've specified the learning rate to 0.001. This is something you can always adjust, but it's always best you ensure you have a learning rate that is not very high. You ensure that you don't have a learning rate. I'm sorry for that. Just someone next door. But ensure your learning rate is as low as possible, but it shouldn't be very low to avoid cases of overfitting, because the network, yeah. So this is something you can always play around after you set it to an initial value like this after training, and then you see your model is not really performing well. You can always adjust the learning rate. So that's it. So then after we've already configured our model, the next thing is just to perform some data pre-processing. So in this case, we're going to create an image data generator that is going to create batches. That is, so in this case, what we'll be doing will not be feeding all the images to the neural network. What we'll be doing will be feeding them as batches. So we're going to rescale these images, and then after rescaling them, we'll create a batch. So you can use a batch of 16 images, but in this case, we'll use a batch of 32. A batch of 32 images. So that's what we'll be doing here. First, we'll be rescaling the images, and then number two, we'll be creating a batch. So for the train generator, because we'll create two generators. For the train generator, we'll have a batch size of 128 images, and then for the validation generator, we'll use a batch size of 32. And since we are using a binary cross entropy for the loss function, the class mode will as well also be binary. Then the other thing, the images, I want you to remember, as I had said, as you can see, the input shape of our input layer, it's 300 by 300 by 3. The 3, as I said, that's the colored image. So we also need to specify here that the target size for our image needs to be 300. Needs to be 300 by 300. So as well, that needs to be specified, because otherwise will not be able to load images into the network. So after defining our data generator, the next thing is just to perform a training. If you've used Keras, once you see model.fit, that should tell you now we are ready for doing a training. So we need to specify our train generator. We need to specify a validation generator as well. And then we also need to specify the number of epochs and the steps per epoch in each. So verbose, these verbose, the verbose here just specifies like, sorry, someone speaking? Hello? Hello? I heard some noise. I don't know whether it's someone speaking. Hello? Okay. McKenna, was there someone speaking?
No, you could just go on.
All right.
If anyone has a question, they will just type it on the chat.
All right. Okay. Oh, so I need to run. I had not run that cell, and then we'll have just to run this cell. So now this is just going to perform the training. We have 15 epochs. The other thing, ensure by default Colab uses GPU, but you can always confirm whether it's running, it's using a GPU. But in this case, you can see we're using GPU. You can always confirm that in case it's using CPU, and you can always switch to GPU. So we're just going to give it a minute or so for it to perform the training. Shouldn't take long.
Oh, Josh, in the meantime, I have 2 questions.
Okay.
The first one is about activation functions. How do you determine which activation function to use? And then the second one is on the data processing. Do you also a similar question? How do you determine the type of processing that is required? Is it more of a personal choice, or is there a set of rules that is followed as to how you should process the images?
Okay. So on the question of the activation functions, so it depends on the nature of your model. Like, for example, if you are having values that are ranging between 0 and 1, a sigmoid activation function will be best. Or so, and we have different sigmoid activation functions. Like, there's this sigmoid activation function, and then we have the sigmoid squashing activation function as well. The values, they range between 0 and 1. So if for a binary classifier, a sigmoid is best choice, because like in a binary classifier, you either have a 0, or you are dealing with only 2 values, and that's the same thing with a sigmoid squashing. With a sigmoid activation function, this sigmoid activation function, it's the sigmoid squashing function. Then so essentially it depends on a particular layer and what is happening in a particular layer, you see. So activation functions are chosen based on the model you're building, and also on what is happening on that particular layer, and the output you need on that particular layer. Then the other question was on the choice of preprocessing, if I got you right, McKenna.
Yes, it was. My question was, when it comes to data processing, how do you determine the type of processing that should be done? Is it a personal choice, or are there a set of rules that govern that?
All right. So as well, it depends. Like I'll give a simple example. Like when building a model that in which color it doesn't affect. Like the applications of a particular model, color is not a fact. It doesn't matter what color it is. You're fine whether it's you're dealing with either grayscale or colored images. Doesn't matter. In that case, you can always convert it to a grayscale image, so that the color feature is not prevalent during the training of the network. So as well, again, it will determine on the usage of your model. That will be one thing. How you plan, how rather the consumption of your model will really determine. Number two as well, the size of the shape, the way you've defined your neural network. If, for example, I had specified this to 224 by 224, then I'll have to ensure that the size of my images will as well conform to the input shape as well. So the pre-processing will determine on the model you're building as well, and the kind of data you have. And sometimes you'll always have to play around with these. Sometimes you'll always have to end up playing around, tweaking some features just to see the different. Like you might build this model and then using colored images, and then you try the same with grayscale images, converting the images to grayscale, and see evaluating the performance as well, and see how it performs. Like for example, in the case of where you're building a model for something like OCR, the optical character recognition. In that case, color doesn't really matter. You can just work with grayscale images, because you just need to identify the characters themselves, and it's essentially not about whether the colors are in blue, red, green, or yellow. So the thing is, it depends on the nature of your model, the applications, and also how you've also defined, or rather how you've configured your model. Not sure whether that answers your question correctly.
Yes, thank you. Both my questions have been answered.
Okay, so we've finished running through the 15 epochs. And one thing I would like you to look at the metrics we have on the screen. We have the loss, which has been decreasing down from 7 all the way to 0.0021. That whatever we have, or sorry, let me say this again. What you're always looking for when building a neural net is to have a low value for the loss function. Should always give you a low value as you progress. So that looks fine. And as you can see, the accuracy goes up and the validation loss should go down as well. So this looks pretty good as well. So what we can do is we can just like try and test the model. The seed time is far much spent. So what I'm going to do, I'm going to download an image of a horse and an image of a human being, and try an image of a horse and an image of a human being, and try seeing whether the network can be able to identify whether this is a horse or a human being. So I'm going just to save this image. Maybe I can just call it horse. And then we can just test it. So this is just a random image on the internet, and then test it and see whether it works. So as you can see, it just tells me this image that I uploaded, that's a horse. We can try out another file. Can try out a human. Images. Let's out these. Save images. So let's test it out and see. Oh, so It says this image is a horse. I did that intentionally. But yeah, so you can always try retraining these, but I'm sure it can detect a human being as well. Let's try getting a human being, the image of a human being, and see whether we can be able to find one human person. Let's try this one. Save images. Oh, it's detecting everything as horses. Right. I'm not sure why. I'm not sure it's going to detect this as a horse because of the color and hair. So now this is when you start evaluating whether you should have converted it to grayscale as well. Let's try and see whether this one, hopefully this one is classified as human. Yeah, finally, at least we have one that is identified as human. So, but basically, we can be able to improve these by, you know, in the pre-processing, trying converting it to grayscale, because like the color doesn't really matter whether it's a horse or a human. The features are completely diverse. So those are things we can always play around, converting the images to grayscale, or definitely getting more images for training. And yeah, getting more images for training as well, and that can definitely improve. I can definitely improve. One last thing I would like to do, I know I've used a lot of time, more than I should have, so I need to fix this. So one final thing I would like to show you is just show you different images going through the different layers. Remember how many layers we had? Yeah, just come back on top here. So we have this layer, that first convolution layer, the second convolution layer, the third convolution layer. So just seeing how the model captures different features on the different layers. So these definitely should be able to give you an aspect of what the model, what the network is learning. So like in the first convolution network, you can see, and that's why I'm saying maybe converting the images to grayscale might a little bit help in helping the model learn, and maybe that's something you can definitely go out and try out and see whether converting the images to grayscale might really help, because as the model is really trying to capture some differences in color and that, and then you can see what happens in the max pooling layer, in the other convolution layer, and like that. So basically that's how we create a neural network, a CNN in Python. And if there's no other question, Makena, I would like to give back to you.
Okay, thank you, Josh, for that interactive session. We were able to follow through as you are doing we were able to follow through as you are taking us through the example in Python. And I do not see any other questions, so I'll ask Eric to take us through the R code lab.
Sandra, just before
Yes.
Eric comes in, can I just clarify something?
Yes.
Yeah, someone had asked why people prefer to use the max pooling technique as opposed to the other ones. Well, and I've realized I usually use max pooling a lot because of the data that I have. So the technique you use will depend on the data you have, because with max pooling, We use it when the images we have darker backgrounds, and then the pixels of the images, the ones that we're interested in, are lighter. So max pooling is recommended in that case because the backgrounds are darker compared to the pixels of the image that we want to use. And the reason why we would it's recommended to have the images having the darker backgrounds and the lighter pixels on the image is because that one reduces computational costs. So that's why max pooling is recommended, because it helps in reducing the computational cost for your model. I hope that's a better answer.
Thank you. Yes, that makes a lot of sense. Thank you for that answer and also the clarification. Yeah, if anyone has any more questions on that or anything else that has been shared so far, please feel free to just type it on the chat and your questions will be addressed. With that said, I'll hand it over to Eric.
Hello, Sandra. How are you? Am I audible or something?
Yes, we can hear you. Please go on.
Awesome, Sandra. First and foremost, want to thank everyone who took time to attend here, and my fellow colleagues, Glorious and Josh. You've really done a really good introduction. I could not have done it better. So thank you so much to Glorious and Josh, also Sandra for moderating this session. So I'll just jump right into the R session. So I'm using a virtual machine to run my code. So maybe Sandra, could you confirm if it's visible? I'm not sure if it. Please confirm on that.
Yes, we can see what you're sharing.
Awesome. So yeah, I'll be taking you through the R session. Mostly it's trying to replicate what we have done in Python in R, and you'll find that the code is almost similar. This is because when they were implementing TensorFlow in R, they just wrapped the whole Python using R wrapper. So behind the scenes, it's Python which is working, but using R wrapper. So you'll find that there's a lot of similarity with what I'll say and what Josh has said, or what I write and what Josh will write. So welcome to my session. So let's start by loading the libraries required for the session. So we'll be requiring some packages in EBI image. This for basically displaying images, can do some pre-processing, but yeah, so that's EBI image, similar to, I think, SciPy in Python. You're a Python Advanced user. You have the tidyverse. So the tidyverse is what we use mostly in R for, data science. The whole data science process really makes data science easy and fluent and fun, I think. Yeah. So, and then we'll be requiring Keras, the Keras interface for R. So if you don't have these packages, you can have them installed as this. So you can have the whole tidyverse installed. Tidyverse is a universe of packages, so you can have them all installed as this, like that. You can also have the EBI image libraries installed like that, and the Keras interface to R uses TensorFlow engine by default. Yeah, so there's a very neat documentation on how to install the Keras interface for R in this link that I've provided here. So yeah, it will be somewhere here. I've displayed the page. Now you have to install some stuff like Anaconda, because which you install for the Python. As I said, this is just R wrappers calling on Python in the background. So without further ado, let's get rolling. So we'll be used as my predecessors Glorious Buyanzi and Josh have said, we'll be using convolutions, to try and predict or classify complex images. So we'll build a horse or human classifier. So this is binary classification because you have only two outputs. So which will tell us if our image contains a horse or a human. So, but the most interesting part here is that we'll be using convolution. So convolutions are just, just filters that try to extract features, and then these features are mapped to a particular label. So yeah, I will explain that in a short while as we go down. So as Josh did, we are getting an external data set from Lawrence Boroni. That I should just mention him. Yeah, so I've given the links to where you can get the data here, and then you can just download them. I've already downloaded them on my PC. As you can see them, the validation and the horses or humans, and then you can just extract them to just a folder where, I mean, a directory where you see we see dim for this. So this just this just downloading data and just extracting data. So once you have the data, you'll notice something. Just as Josh has said, this is the data set. So just a folder, for instance, that has we'll be using our training. This is a training data set. So the training data set has two subfolders, horses or humans, and you can see some of the images here of horses and some of the images of humans. So as you notice, we have not explicitly labeled this as horses or humans, but we have a powerful preprocessing tool in TensorFlow that is known as the image data generator that will do the whole cumbersome work of labeling these images as horses or humans depending on the directory name. So once you get that, so this is just easy code of just displaying the number of images we have. So as you can see, we have 500 training horses images and 527 training human images. So I'll just take random pictures at random using the sample R command. So the sample R command just takes images at random and just displays them using the EBI image function. So after we have picked random images, as you could see here, just as we have picked 8 random images of both the training and horses, we can now display them using the EBI image library, to obtain something like this. Hope it's still visible. Yeah, so these are some of the pictures we'll be using. As you can see, these are very diverse pictures having diverse colors. So what we're really trying to do, the gist of today is, lost me, sorry for that.
Yes, that's where you are at.
Yeah, I'm so sorry for that. Yeah, as I was saying, some of the images are really diverse, different postures, different people, different color. So what we're trying to do is really use convolutions to extract features so that we can correctly label this as a horse that only has the muzzle in view, and this that only has all the limbs in view, and also a picture like this that has only the behind part in view. So this is what is really the gist of convolution neural networks, just extracting features so that if we could extract these pointed ears, we could say, the computer could know that these pointed ears indicate a horse. So that's what is called feature extraction. Yeah, so let's go down. Oh, sorry. Cancel. So let's go to now doing this in code or something. So let's now build a small model from scratch. So very quickly, now really repeating what Gloria said, a convolution is just basically a filter that passes over an image, processes it, and extracts information so that if an image has certain features, it belongs to a particular class. If an image has hooves, for example, it belongs to a horse. If an image has a small nose, maybe it's a human or something. So pooling, as Gloria's really explained well, reduces the amount of irrelevant information, but still maintaining the prominent feature. So I'll just start by loading the required packages, that is the tidyverse and Keras. And that's how you load it in R. So, and then we are going to instantiate a convolution. So convolution neural networks are in batches, divided into 3 parts. So there's the first part is the convolution part that does convolution pooling. And then we have, you have the convolution, you have the poolings, and then you have the dense layer that goes after the convolutions. So after the convolution layers extract features, they pass them down to the densely connected neural networks, which now classify these pictures as either, a horse or a human. So yeah, let's do that. So we start by Sandra. Could you give me a minute? Just a minute.
Okay.
Hello, Sandra.
Yes, Eric.
Yeah, sorry about that. I think I'm having some internet issues, but yeah, let me just try and rush over through this. So as Josh explained, a Keras sequential model is a model which has subsequent depth of layers. Maybe just like this. This is a sequential model, something I think Josh had already explained. So we start first by defining Keras model. So we say give a name a model, call it model 2. So model 2 is equals to Keras model sequential. In R, we read this as then. So one thing to note, just as Josh said, is that the first layer of the convolution layer, you define the input shape. So when you go down research, you realize that convolution neural networks operate over 3D tensors. So an x by y, which is the size, and then a color depth of 3. So that's this is the reason why we're putting this command. So input shape 303. Then we define the number of filters. So here I've started with 16. So 16 filters in the first convolution layer, and then the kernel size and the activation layer, the activation function, which is ReLU, which I think by Josh and Buyanzi have really explained. So we pair the convolutions with max pooling. So the max pooling halves the dimensions of the output of the first convolution. So this will reduce the amount of information that the processing work that the model will do. It also helps minimize overfitting. So, and then we define another convolution layer with 32 filters, another convolution layer with 64 filters. So we just pair a convolution layer and a max pooling, a convolution layer and a max pooling. Yeah, so after you're done defining the convolution layer, now we assign a classifier to the convolution. So as I said, convolution layers learn the features and then pass this to the dense layers, which then map the learned features to the given labels. So our next step will therefore to define a densely connected layer so that it can classify the features that have been extracted by the first convolution layer. So I've put some links here, for people who are new to this stuff of activation functions and all. So the Keras website really also provides a good explanation of all these activation functions found in Keras. You can find it here. So yeah, please look at that at your own time. So after that, this is the step where we assign a classifier to the convolution networks. Where at first we flatten the output of the convolution layer. As I said, the convolution layer operates over 3D tensors, an X, a Y, and a color depth. But the dense layers usually operate over 1D tensor. So this is the function of the layer flatten. Then we add some dense layers of 512 neurons with the activation function that's ReLU. And then the output layer, we can get away with one output layer which uses a sigmoid activation function. As Josh explained, the sigmoid varies values between 0 and 1. So a value that is close to 0 will be a host, and one that will be close to 1 will be a human, because of alphabetical host human. Yeah, so as you can see, the model summary, the max pooling really reduces the dimensions of the preceding layer. So yeah, for reasons that have been explained before. So after that, it's now time to configure the model for training. So here we define some parameters such as the loss. So the loss will determine how well our model has, how well our model has classified either a host or a human. And then after using the loss, we go to the optimizer. So the optimizer is the one that changes the weights so that they can guide the neural network to classify better. So after we get a loss, after we determine our loss, if it's a big loss, we'll change the corresponding weights of the neurons, so with an aim of getting a better classification. So the learning rate is the step size that the optimizer will use to optimize the weights. So a very high learning rate, you'll not get to convergence faster. Very low learning rate, you'll take a long time to really get the best weights. So here it's just trial and error. There's no really defined way of doing this. So the loss is binary cross entropy because you're using binary classification. So if we had more, you'd use something like categorical cross entropy. So RMS prop is also a good optimizer, but I like it. I've used it a lot of times, so I think it's a good optimizer. But also some optimizers are like Adam and Adagrad, which have automatic learning rate adaptation. So you can check on that and see how well they will help in classification. So let's now do some data pre-processing. So there are quite a number of processes that we need to do before we can get the data ready to be processed by neural network. So you have to read an image first. We have to decode the JPEG context to pixels. We have to convert them to floating tensors. We have to normalize them and auto-label them. So this can seem like a daunting task, but the image data generator really does a good work for us. And this is how it's defined in R. So the first is we put a pre-processing step, that is which will rescale our images, so that we can avoid stuff like very large images, they'll bring a lot of computation work and also could introduce bias. So that's why we rescale our images to smaller dimensions. And then we'll now define a generator which flows the images from these respective folders. So we'll just flow images from these respective folders to the neural network. So we'll first define a directory. So we're telling our neural network, please flow images from this directory, and then pre-process them using the generator train data gen, which we just defined here. So the only pre-processing we do is rescaling. And then the target size is 300 by 300. So please make sure that this is the same as what you defined as the first as the first as the first as the first feature in our first convolution layer. They should match, so that our neural network is expecting 300 by 300 images. So the images being flowed out by the flow image generator should also be 300 by 300. And then also flow them in batches of 128. So 128 images at a time that are fed into a neural network. We find the loss, we optimize the weight, and then yeah, we continue. So that's what we'll do here. So that's what that does. So that's for the training. That's for the training generator. We also use for we also do the same for our validation generator. Just the only difference is just change where we want the validation data set to be flown from. So this is the only thing that will change, but the rest remain constant. I mean the same. So yeah, now time to train our neural network. So yeah, so in R we will train the neural network using the fit generator. So the fit generator first obtains image from the train generator. So the train generator is the one that is flowing images out of a directory in batches of 128. So the steps per epoch. So one thing to note that a generator generates images, flows images out continuously, non-stop. So how do you determine that an epoch is over? So an epoch is the number of times our model will go through the data. So the steps per epoch are 8. So this means that receive 128 images 8 times. So gets the first 128 images, flows them through the networks, obtains the errors, determines the weights, and then takes another 128, does that 8 times, so that declares an epoch over. And then after that, it takes a validation data to see whether its accuracy, to test its accuracy. It also does the same 8 times. And then we'll do all this process of, taking data in batches, validating. We'll do it 15 times. So that's the number of epoch. And then this verbose just tells, it's just an output for what you want Keras to display. Yeah, so I'll first reach there, and then we have assigned the output of the model to a variable named as history. So first, yeah, maybe Sandra, if I could take some questions before I continue, if there are any. Hello, Sandra.
Yes, just a minute. Why do we increase the filters as we go down the network?
Oh, awesome. That's a pretty good question.
I'm getting this.
Just a minute. Let me go just up there. Yeah, yeah, here I started with 16 filters, and then that's 2 filters, and then 64. So as you realize as we go on that the filters, as you go down the neural network, you see that there's this aspect of the max pooling really reducing the dimension of the images. So how we increase the number of filters is because as you go down the network, more abstract features are being extracted. So you'll see like there's a filter that will focus on the hoof. You see that's really small, maybe compared to the muzzle. So as you go down the network, more abstract features are being extracted. And so we need more filters to encode like the very small details and the more complex details. So that's the only reason I choose to increase my number of filters as I go down the network, so that I can encode the really small details that are being focused on by a network. And this I'll show this as I really go down the example. That there's a place where I'll show this how an image goes through the network. Yeah, so I hope I've answered that, Sandra.
Yes, you have. Maybe another question would be, how could we improve or increase the accuracy?
Awesome. Let me just answer that after I've explained this. Just a minute. Just hold that thought. So after our model trained, we see that we have a loss of 0.2916 and an accuracy of 1. That is for the training images. And then for the training set, for data it has never seen, it has quite a high loss of 2.213 and 0.7266. So this is a characteristic of something known as overfitting. So our model attains an accuracy of 99%, but doesn't perform so well on data that it has never seen. It performs like 73%, which is really quite low. So overfitting is something that occurs when the model is trained on very little data. You see, like us, we trained on using 500-ish images. So yeah, there are some techniques to increase the accuracy. One is known as image augmentation. So just image augmentation just randomizes the data, maybe rotates the images, zooms the images, shares the images, But that's really beyond the scope of this lab. So, but if you'd want to find ways of how you can improve accuracy, there's also something known as adding dropout layers. So in dropout layers, we remove some of the neurons, so that we can minimize interdependence of like this of neurons, such that a neural network will only store very less information, such that as the neural network trains, some neurons are like assigned to a certain feature, such that these neurons are like, if you see pointed ears, that's a horse. If you see who maybe vertical lines, maybe those are most likely human legs. So if we remove some of this interdependence, an image of a horse could only see two limbs, and if we see that interdependence of neurons, these two limbs could be classified as humans, and they are horses. So the gist of removing the gist of using dropout layers is just removing the layers that to prevent interdependence of neurons. So I'll share a link at the when I'm finishing, so that we can you can see how you can improve the accuracy of this. So time to generate predictions of new data. So I've downloaded some images here to test the neural network. So I hope you can see my images. So I have one horse which only has two limbs highlighted, a man, this lady, and this horse. So let's see if our neural network can be able to classify these images correctly. So fingers crossed. Let's see the type of work it will do. So just run that and this, and then we can view the predicted results as view the predicted results. Oh, nice. So horse 1 has been labeled as a horse. Man 1 is a human. Man 2 is a human. Woman 1 is a horse. Woman 2 is a human, and the horse is a horse. So I think our neural network has really done a great job in, even though the accuracy was a bit low, I think it has done quite a recommendable job in classifying the images. So maybe this lady was classified as a horse, this is something that we're calling like overfitting. So maybe the neural network, so this maybe the feature it extracted was like the long hair. So it like so like the long hair is like maybe characteristic of a mane, maybe in this horse, and that's why it classified this, could be the reason classified this woman as a horse. So yeah, these are stuff that we can improve on using data augmentation and robot layer. Yeah, so I think I'm almost done, because just the next step is seeing how an image traverses through the neural network. So I've just picked a random image, and I'm passing it through the neural network and to see how it's being transformed by the convolution neural networks. So this is our image through the first convolution layer. As you can see, the different 16 filters highlight different stuff. Maybe this one is highlighting, I'm seeing the limbs mostly. This one's like transforming it into a heat map or something. Yeah, so the different filters do different extracting of features, and then they are passed on to a max pooling layer. So the max pooling layer really focuses on the important parts that were highlighted by the upper layers. So as you'll see this example, yeah, then this is passed on to the other convolution layer, and also the other convolution layer extract different features from it. Some are not even visible, so you can see something like this. The neuro this filter is focusing on the outlook on the outline of the horse. As I said, that's why we're increasing the number of filters, so that very abstract features that are such as in this filter that we cannot even see can be captured by the neural network. So with more filters, we'll be able to capture more features. So yeah, so that is how the image traverses through the network. So, and maybe a summary, just a small summary. So as the image goes down deeper the network, the outputs of the layers become really abstract. You see, like in some filters, you won't even see something that you can see with your naked eye. So, and they become less visually interpretable. So the representation downstream start highlighting what the network pays attention to, and they show fewer and fewer features being activated. So this is known as sparsity, which is a key feature in deep learning. So as you see, as you go down the neural network, high representation carry increasingly less visual information about the content of the image and more refined specific information such as the hoof or the muzzle or the limbs. Yeah, so this is why convents are known as distillation pipelines, because raw data gets in, it's done a lot of transformation by the convolution network, such that the information going down to the deep neural networks is more focused and highly more accurate. Yeah, so that's how you implement convolutions in R. And yeah, I'll be open to any questions. So if you'd want to see how to increase the accuracy, you can go down to some of the to rpubs.com. There's a piece I wrote on how to increase the accuracy of convolution neural networks. So here it is, image augmentation and overfitting. So you can see how you can implement image augmentation. Also added how to implement dropout layers. So this is how you can increase the accuracy of neural networks. So Sandra, thank you so much. Thank you so much everyone for listening to me. Sandra, I hand it over to you.
Thank you so much, Eric, for that walk through the R code. If there are any questions, still feel free to ask them. You can unmute or you can type them in the chat. But generally, I just want to take this opportunity to thank all our speakers, Eric, Josh, and Rianzi. So maybe if you guys could share your contact details or how we can reach you if we have a question on the same. That now goes to our speakers. Like maybe you could type in the chat how we can reach you if we have questions. Does anyone have a question before we conclude this, before we end the session?
Hi. Actually,
Hi.
Actually, I couldn't have access to the chat.
Oh, okay.
Yeah, it says chat in channel meetings is only available to team members. So I have two questions. So can you send us the actually collab, the links to the markdown and the collab? And is there a recording, you know, of this session?
Yes. We will be able to send you all the resources that were used during this session and also the recording once it's out. It'll actually be posted on YouTube and we'll be able to send you guys the link. Just a question, did you RSVP for the event? Because I guess everyone who did, we have their emails.
In the meetup, right?
Yes.
Yeah. I already did.
Okay. If you did RSVP, then you will definitely get all the resources that were used in this session, and also the link to this recording.
Okay. So I have another question actually about which of R or Python is more efficient, you know, for like deep learning and CNN.
Okay. Thank you for your question. Eric, would you like to take that? I think both Eric and Brianzi could give their input.
Yeah. Hello.
Hello.
Thank you. Thank you, Fatma, for that question. So I mostly use in my opinion, I think Python had the like initial rerun, in deep learning and all. So there's still a lot of resources for doing this in Python, just as Josh did. So that's why most people go to Python. But I think R is also coming up quite nicely. For instance, we have R versions of TensorFlow. Last week they launched the R version of PyTorch. So I think what we're really trying to do in this session is just give everyone just an option. An option. You can either use Python and R. I think they're really good languages. I love both of them. So I think, Fatma, it really narrows down to you as an individual. Do you prefer Python? Do you prefer R? Because I think at this point both of them can really do can really do what the other can do. So yeah, but in my opinion, I'm an R person, so I'd go for R. But I think also Josh should go for Python. Let me hear what you say. But my takeaway is, if you feel like Python is really the one for you, please go ahead. There's R, there's also MATLAB. I think it just depends on you as an individual, in my opinion.
Thank you very much. Actually, yeah, I use a lot R and Python, but I'm more R fluent, so that's why I'm asking. Is R slow, you know, when it comes to deep learning, or is it like Python, you know?
Awesome, Fatma. I think now that makes two of us. I'm really pleased to meet you. Yeah. Anyhow, yeah. So like with the upgrade in hardware, such as use of GPUs and everything, I think the speed is quite good. And also you can opt to use the Microsoft version of R known as MRAN, which supports multi-threading, and this will make the computations much faster. But so I think with the coming up of Microsoft R Open and resources such as GPUs and TPUs, computation for R is at least at a level where it can be considerable to Python. Yeah,
Okay.
that's my opinion, Fatma.
Thank you very much. Thank you.
You're welcome.
Yeah, it's really an amazing workshop. So I really enjoyed it. Thank you very much.
You're welcome, Fatma, and we hope we can see you in future events.
I hope so. Thank you.
Okay, thank you for your questions. Does anyone have any question? Please feel free to unmute and ask your question if you have any. Josh was on the call, but I guess he had to leave. Yeah, so if anyone has any other question as we conclude. Okay. I don't see anyone attempting to speak. So yeah, I'd just like to apologize. I was not aware that the chat was not accessible, but we'll try and make that possible on our next call so that you can either unmute and ask your questions and clarifications, or you could type in the chat and you can be able to easily access the chat. Okay, I guess with that said, I'd just like to thank our speakers for taking the time to take us through convolutional neural networks, and also to you guys who took your time to attend the workshop. It would not have been possible without you guys, and sticking till the end. That's very, very commendable. And all the resources will be sent to you guys. That's the resources used, the links to the code labs, and also the recording of this session. So with that said, I'd like to wish all of you a lovely night, depending on which part of the world you're in. And I hope to see you guys in our next event, which will be, in 2 weeks' time, where we'll be talking about RNNs. So stay tuned and see you then. Feel free to leave at your own pleasure.
Thank you, Sandra, for having us. And thank you to Josh and Glorious and to everyone who attended. You guys are really the best. So see you soon.